Ivanovic from Astronomical Observatory of Belgrade, who will tell us about the nearly circular orbits of galactic disks. Slobodan, please go on.
Do you hear me?
Yes, perfectly.
Unstable. Your internet connection is unstable. Oh, perfectly. Now you hear me. No problem.
Yes, yes,
So I can start. Oh,
yes,
thank
please
you.
go on.
So circular orbits are orbits with a constant velocity magnitude. Of course, the form is a circle. They are possible in stationary and axial symmetric potential. Spherical symmetry is a special case of it. In other words, when the specific energy and angular momentum, at least one component, are conserved, a nearly circular orbit is a generalization of a circular orbit. Uh, Very simply, the initial conditions are a little bit varied. So now it's not exactly a purely circular orbit. And then we have the question or a task of stability of an orbit. Really, this is a question of stability on initial conditions. And the condition which I just have mentioned is just a necessary one. Whether it is sufficient or not, it should be checked. Of course, the method is very well known, is to reduce the problem to differential equations to the form, to put them to the form of linear harmonic oscillation. The result is sufficiently well known, but there are two questions which arise, and they are solved here in this presentation, in this paper. This is the correctness of the procedure and to what degree an orbit of a star, which is a nearly circular, obey the harmonic oscillations, the sinusoidal law. First of all, I think it's the best is to mention eccentricity. Eccentricity can be, of course, defined in very much and a very large number of possibilities. A lot of possibilities define it. Nevertheless, I refer to use the classical definition. This is the difference of the two extremal distances divided by the sum. And this is a dimensionless quantity, which is between 0 and 1. Nearly circular means that the eccentricity is very near to 0. So now we have two integrals of motion, or quasi-integrals, the energy and angular momentum, specific energy and specific angular momentum. And in this procedure, it is important to determine the connection between the energy and angular momentum one side to the eccentricity and mean distance, this is arithmetic mean, on the other side. And this is done by using a technique of power series. And finally, it depends on the fact whether the circular at the if it increases, then for example, we can use just as if it were purely circular motion. On the other hand, for the angular momentum, which is important to say, has not been written in the literature, that there is a term depending on eccentricity square. And the such angular momentum is, of course, lower than that corresponding to the purely circular motion. The coefficient multiplying the square of eccentricity in the case of increasing circular speed at the mean distance even does not depend on the particular behavior of the circular. It's always equal to 2. But if it, we can say that in the case where we have neither decrease nor increase, then the situation is the same. The two expressions uh, obtain as the same force. The limits of the application of the sinusoidal motion, sinusoidal which characterizes linear harmonic oscillations. I can say that even for a moderately high eccentricities, not too low, it's even possible to notice that the sinusoidal law is evidently not effective. Really, there is a difference in the time distribution within the semi-period. In the first part, between the minimum distance and the mean distance, it's shorter than the second part between the means of usable to add a new term. And really, what I have done this and obtained an improvement. So I can see of a test particle moving around, not exactly circularly, but in a nearly circular orbits. On the other hand, the ratio of the periods, I think the period of the circular motion and the animalistic period of distance, it is practically the same. It, of course, is changed, but the changes take place only for some eccentricities, about say one half, or no, not so low eccentricities. And for the low eccentricities, the situation is rather well known and very simple. The Milky Way, for example, and not only for the Milky Way, it's also for the case of other spiral galaxies. We have so-called thin disks, and the motion of typical thin disk stars is just a nearly circular motion, where it is possible to consider its motion perpendicularly to the main plane independently of the motion uh, with projection to the main plane. And then it's very useful to have correct, say, of course, approximate expressions for the angular momentum and energy, but which are correct and which are applicable in the case of a study with the aim to, for instance, determine some problems or the comment the ratios of the square of velocities, I think random velocities, then we can use this very easily and obtain interesting results. And also now, of course, it's a topic of another presentation, my colleague Dr. Milan Stojanovic on Friday about our plan and our study of the orbits of nearby stars. The data for these stars are given in Gaia and the modern catalog, and we plan to form a basis or a database concerning the orbital elements. This is an approach which is, of course, more rigorous. It's not so simple. The orbits are studied as if they were just normal spatial orbits. Nevertheless, it is possible to see for the typical cases of a thin disk, like our sun, for instance, the orbit obtained in this way, strictly, is practically just what one can obtain by using the approximate approach. and we can see that it is an important question. This, I think, it's enough for this time because I have unfortunately no presentation with formula, but I think this is not so necessary. It's possible, of course, to present in the proceedings to be seen. So if there are any questions, I'm ready to answer any comments, please.
Thank you, Slobodan. I invite the participants to raise their hands in the Zoom window if they want to ask a question or type it in the chat window. We have time for
Oh,
a few
yes. Oh,
questions.
yes, it's possible to type them. Mhm. Yes, yes, I see the chat window.
No questions in chat box and no raised hands.
Yes. Maybe we can we can just move on. Thank you, Slobodan, for this nice lecture. Um, the next speaker is Dr. Monika Jurković, also from Astronomical Observatory of Belgrade.
Oh,
Monika,
thank you. Also,
Monika will tell us about type 2 and anomalous Cepheids. Monika,
Thank
please
you
go
very
on.
Yes, thank you. Let's see this share screen. Share. Do you see my screen?
Yes.
Thank you. Let's try this.
Yes.
So thank you very much for having me on this conference. I'm going to talk about type 2 and anomalous Cepheids, which were actually my PhD thesis. So why is it important to study pulsating stars? Because type 2 Cepheids and anomalous Cepheids are pulsating stars. It is important because Cepheids are the cornerstone of the distance ladder. And here is a graph showing the distance ladder. It is from Adam Rees. If you look at the bottom half of the graph, you can see, if I put it in focus, that actually what we want to see is at this beginning of the calibration. So once we have the distances for the Cepheids, then we can calibrate them for the nearby galaxies. And those nearby galaxies are then calibrated. I mean, the Cepheid distance calibrates the supernova distance and so on and so forth. So this is like the cornerstone of the calibration. There is huge debate about how exactly is it done. Is it enough what we have done? Because there has been new research connected to the age naught, the Hubble constant. And one of the things that people are trying to examine is whether the distance calibrated from the Cepheids is the one that is causing the problem. It looks like that it's not, but we cannot be sure. Why am I talking about Cepheids in general? I'm talking about Cepheids in general because they are also pulsating variable stars. And as you can see, the pulsation itself is something that is intrinsically characteristic for the stars that are changing. And if you look at this graph, you can follow the variability tree. So you have variable stars that are changing because of their intrinsic changes in their inner structure. And if you look then in the stars, you can see pulsation. And if you follow down this road, then you can see that there is a branch that contains R Lyrae classical Cepheids, type 2 Cepheids that are shown here in two separate branches. So the study, what I study are actually type 2s and anomalous Cepheids. So if you plot these pulsating stars on the Hertzsprung-Larsen diagram, and this is like a classical way of showing the intrinsic changing stars on the Hasselblad diagram, you can see that the type 2s and anomalous Cepheids occupy the so-called instability strip, which is seen here with these dashed lines. And also what you can see is that the classical Cepheids also occupy this space, as well as the R. lyrae, which are down here. What makes them different is actually their mass and the phase in their stellar evolution. So these are not same, but they are doing something similar. And all of them, so the classicals, the R. lyrae, the anomalous Cepheid, they all have a so-called period luminosity relations that is used for the calibration. So what do we study? So what can we observe and what to do with it? First, let's make it clear what type 2 Cepheids are. So type 2 Cepheids are pulsating variable stars with a very low mass, 0.5. That means that they are very old, at least 10 gigayears or maybe even older. They can be subdivided into 3 subgroups. The division is mainly due to the statistical divisions that can be seen in the observational data. What you can see here are typical light curves for the BL Hercules subtype in the first 2 panels, then the W Virginis, the next 2 panels, and the last 2 panels are RV Tauri stars. The W Virginis stars occupied the period space between 4 and 20 days, and the RV Tauri stars occupy the space between 20 and 100, 150, or even more days. It's not clear where the upper limit is. As also you can see, there are many things that these stars do. It's not only that they pulsate simply. The classical assumption about how these stars have same masses but are in a different period range is this plot. And it means that as they start, as the type 2 Cepheids start off from the horizontal branch, they cross the instability strip the first time. That's when you see them as BL Hercules stars. As they progress further on, they develop something called thermal pulses or blue loops that makes them venture again across the instability strip, and that's when you see them as W Virginis stars. As they evolve further on, then they cross the instability strip for the last time, and that's when you see them as RV Tauri stars. The number of non-type 2 Cepheids changes, and it is going to change very, very much in the forthcoming years. So at this point, we can say that from the Ogle 4 in the neighboring galaxies, spheroidal small galaxies, the LMC and the SMC, it's around 350. In the Milky Way, one of the older catalogs was the General Catalog of Variable Stars, where you can see that 444 are known. And if you look at the Ogle Bulge survey, there is already more than 1,000 in them. There are other surveys. I did not plot all of them. I mean, put all of them here. But you can also observe type 2 Cepheids in globular clusters, but not many. As you can see in the list here, M3 has 1, Omega Centauri has 6, M13 has 3, M5 2, M2 3, M10 1, and M80 1. So observing them in globular clusters is not as trivial as it sounds, because it takes a lot of time. As you have seen, their pulsation period can be quite long. So it means that you have to observe the same object for a very, very long time. And there are other galaxies that have type 2 Cepheids, which means that in the future, we can actually calibrate the distance ladder scale with them, I hope. The anomalous Cepheids are a little bit different. They have masses of 1.2 solar masses, and they're a little bit younger, from 1 to 5 gigayears. What makes them special is that they are metal poor, and that is a strange feature of them. They pulsate in a fundamental mode, which you can see here on the right side, F, meaning the fundamental mode in the first overtone. So the two modes means that the light curve shape is a little bit different. The number of them is rising, and we can say maybe 100, 200 is known. It will change also as observations continue. They're not, I mean, observations can be done from the Earth, like the long-term observing projects like OGLE or the VMC or the North Star Variable Survey or the Catalina Survey. Now the new survey that is producing new stars is SSSN survey, and then there's Pan-STARRS as well, and others. From space, there have been Corot observations. Corot was specifically a mission to observe astroseismology, but then there was one classical Cepheid which turned out not to be a classical Cepheid in Kepler, but in K2 there are many type 2s. Then there is the integral OMC survey. It is very strange because integral is not not designed to observe variable stars, but it has a camera that is observing variable stars. Is very useful. There are observations with Hubble, and there are observations with Gaia. So when we observe them, what is it that we have to be very careful of? We have to have in mind that observing variable stars in different filters means that you see a different light curve. So when it comes to classification, for example, it is very important to keep that in mind, that different filters produce different light curve shapes. So what can we learn from light curves? As for one, we can have a classification, which is not a trivial step, and I'm not going to go into it. But if you have the right classification, then you can guess the mass, age, and radii of these stars. Also, what you can see from the light curve is how these stars actually behave. So you can observe something called a period doubling, cycle-to-cycle variations, chaotic behavior, which means that you have insight into their inner workings as the stars pulsate. Let's see some examples. So this is the discovery paper for the period doubling done by Radek Smolets in 2012, I believe. So what is period doubling? Period doubling is actually, as you go from one period to another, you can see that the light curve amplitude changes in its upper corner. So the red and the black lines actually represent the true change in the pulsation. The amplitude changes in every second period. So that's why it's called period doubling. This was also discovered in the Kepler data, K2 data. So M80V1 is the W Virginis star in M80, which I have shown before. And as you can see here, the amplitude in the upper and in the lower half of the phase light curve is changing, and this is a clear sign of a period doubling. But if you look at the KT SCO star, you can see that this change goes through the whole light curve, and this is not period doubling. This is something that we would call like a cycle-to-cycle variation. It is not clear what is causing it. Also, this dynamical phenomena is observed in other stars. These stars are from the OGLE database. They are in the Milky Way. As you can see, OGLE BLG represents the bulge. So these are, so the period doubling was observed in the Beal Hercules, W Virginis, Arbitrary stars. There is a period 4 as a cycle. So it's not the repetition is not in the second period, but in the fourth period. And that is observed in Arbitrary stars. And there are other modulations that are observed in the Beal Hercules and W Virginis stars. But in this plot on the left side, you can see something that is very new. It was a result from 2019. That means that the first double mode Beal Hercules stars were observed where the fundamental mode and the first overtone is excited in the same time. So the black line is the observed light curve, the blue line is the fundamental mode, and the green line is the first overtone that is observed. And if you look at another result, also from the OGLE database, you can see that there are now first overtone explicitly first overtone type 2 Cepheids observed in the LMC. So these are the first ones of such kind observed in the LMC. The blue is the phased light curve as it is observed, and the red one is the model that confirms that it is a first overtone. Maybe it is interesting to note that the masses are a little bit higher than we suppose that they are. That's an open question. So what else can be observed? If you look at the anomalous Cepheids, I have a result from 2018 where I claim that F epsilon Virginis is an anomalous Cepheid, and it has something called like a Blaschko effect. As you can see, these dots here and here actually do not align, and this is a very specific characteristic of a Blaschko effect. But then my colleague Emma Shaplahi in 2019 published a paper with K2 observations. She found these anomalous Cepheids, and the first two on the left-hand side are the ones that show Blaschko effect, and it is a confirmed Blaschko effect. The Blaschko effect means that there is an additional change in the amplitude of the pulsation with a secondary period. And if you look at the whole light curve, you can see that it does change. Okay, what can we do? What can we observe additionally? We can do something called a multi-wavelength photometry, which includes a lot of observations from a lot of wavelengths. And then you can do a spectral-energy distribution modeling to get the luminosity effective temperature of the stars. This is how a typical spectral-energy distribution model looks for an AC-HIR. AC-HIR is a known Tauri star in a double system. So here are all the observations with these dots. And we got all these data from a whole lot of databases, including Google Eros Macho, and also additional individual papers, Dennis Tumes SX. There has been some individual infrared spectra, the LMC synoptic survey, the VMC survey, Weiss, Zakari. So a lot of observations went to this. And what is it that we get in the end? We get a Hertzsprung-Russell diagram for the type 2 Cepheids and anomalous Cepheids. And as you can see, so here is in the lower corner, here are the Biela Hercules stars. They fit very nicely with the theoretical instability strip. The blue and the red lines show the different theoretical boundaries for the instability strip. As we move on to the W Virginis and the Tauri stars here in the upper left corner, you can see that they are a little bit different. So new evolutionary models have shown that this is possible too, but not as it is shown here with this model in the red and the black. So this is how a typical period luminosity relation would look like in Western height index. So this is just observed V and I band photometry. But if you look at it with the luminosity, you can see that the period luminosity relation becomes much nicer. And if you can see here, we have actually given the period luminosity relation in the bolometric magnitude, so directly from luminosity. It means that the calibration of the distance ladder can be done much nicely if you find them in other neighboring galaxies. We have also derived the period radius relation, and also these two stars, so the type 2 Cepheids and anomalous Cepheids, because they form a period luminosity relation, it also means that they can trace old and intermediate age populations. So other things can be done with them to follow how galaxies have evolved. And that means that they are useful galactic evolutionary tracers. What I have found, for example, what is very interesting is this phenomenon I called shapeshifting. So if you look at the phase light curve, you can see that these colors code different different stages in the pulsation of the star, and as you can see, it actually changes its shape. It cannot be called a Blaschko effect because the Blaschko effect should not be present in a period in stars with periods of around 15 to 20 days. So it's something different. That's why I called it shapeshifters. Maybe another interesting question is the metallicity of type 2 Cepheids. So the assumption is that type 2 Cepheids should be metal poor because they are old, but in the case of type 2 Cepheids with short periods in the Milky Way, I have actually shown that they have solar-like metallicities. They are not metal poor. So this is an interesting question which needs to be examined further, because as you can see, the measured points here in the black dots are very scarce. So what one needs is more measurements of directly measured metallicities from spectra. If you look, the pink model is actually a metal poor model with minus 1.5 metallicity and a masses of 0.55. But if you look at the, this pale blue line, the model is actually for 0.0 metallicity with a masses of 0.5. So this is an interesting result, which I'm quite proud of. What is the future? The future is the further observations with other space telescopes like TESS, and first results are coming out. We have our paper now submitted to APJ with the first results, and in the future, even bigger observing programs, all sky observing programs, are supposed to bring even more of these observations to our attention. Thank you very much.
Thank you, Monica, for this very interesting review of type 2 and anomalous Cepheids. I invite the participants to ask questions in chat or to raise their hands. Since we have a few minutes, I can ask one thing. If I remember right, there were some indications that a lot of RV Tauri stars are actually binaries, and I wonder if these three subtypes of type 2 Cepheids are actually the same objects passing through different evolutionary phases that we see on the HR diagram as different pulsating variables. Could it be that they're all actually binaries mostly or in part?
Right, this is an interesting question. So we have looked at the binarity of these stars. So there are no confirmed binaries among BL Hercules stars, and there are some binaries among W Virginis stars, and they are called peculiar W Virginis stars. So what happens is that when they are in a binary in this phase, they look like as if their luminosity is higher. So the luminosity of the two stars adds up, and that's why you see them brighter. But I cannot claim that all of the RV Tauris are in a binary. It is very hard to disentangle what is caused by a binarity and what is actually the typical pulsation behavior of these stars. So yes, there are some binaries, but I'm not sure how the binarity is affecting the pulsation.
I see. Thank you. Do we have any other questions? If not, let us proceed to the next speech, which will be given by Dr. Milan Stojanovic, also from Astronomical Observatory of Belgrade, and he will tell us about the galactocentric orbits of the thin disk stars in the solar neighborhood. Milan, if you're ready, please go on.
Good morning. Okay, so share screen, and I hope you can see, right?
Yes.
Okay. So thank you for the introduction. The title is a little bit longer, but This is actually a presentation of my final PhD results. Since it is a tradition to present PhD results on a national conference, I have finished with my PhD almost 3 years ago, and I will just present the main results. Some of the things that I have continued later after this, I will present hopefully on Friday. I just wanted to mention that my mentor is Slobodan Ninkovic, and he presented some interesting, let's say, a new insight into the galactocentric orbits this morning. So let me start with the presentation. So when we talk in stellar dynamics, there are two approaches based on equations of motion and on Boltzmann equation. The subject of the Boltzmann equation is the distribution of stars in phase space, which can also be represented through elements of the galactocentric orbits. These elements are here presented, so you can see the three-dimensional orbits, and as a consequence of three-dimensional orbits, the definition of the elements is not always clear. The projection onto the meridional plane, like you can see here, is something that is well defined and very often presented in literature. On the other hand, the notation of eccentricity, especially in three-dimensional orbits, is not quite clear. So in addition to determine the phase space distribution, we need to be able to calculate well-defined orbital elements for a large number of stars, especially for disk stars. And here you can see a representation of one disk star, of a motion of a star around the center of the Milky Way. And this is how it looks when you look that in XY axis. The median error and eccentricity only for the disk star orbit parameters can be very well represented in this way. So in order to have all the necessary things for my research, of course, we need the rotation curve of the Milky Way. And this is one set of observational parameters collected in one place. This was published in Nature Physics in 2015. So at the time of writing of my PhD, this was the newest collection of data, but also one of the best compilations even today. So here you can see even the let's say 20, 30 kiloparsecs, some measurements, but what we are mostly interested is this part, let's say between 5 and 10 kiloparsecs. In order to do all this work, we needed to choose some kind of model for the Milky Way, and we chose an analytical model with 3 components, which very well fit for example, this observational data here that you can see. This is, of course, 3 components are bulge, disk, halo, and this is the combined combined rotational speed of the for the Milky Way model. If the eccentricity for a star orbit is low enough, then interval, which is, let's say, best presented here, we are talking about the orbits which can fit in between 2 cylinders, between 2 planes, that is well defined, like here. So if the eccentricity is low enough and this interval is sufficiently narrow, then it would be acceptable to assume a power law dependence for the circular orbit for this part. And here is just one example how we can do that, where alpha is a relation between Ort's constant. The procedure for obtaining Rm and E is the same as it would be if the spherical symmetry were valid. And in case of spherical symmetry, these quantities are actually exact integrals of motion, because their consistency follows from conservation of energy and angular momentum. So if a sample of stars were given so that all of them are at the same position, or similarly approximately same position at given time, then the values for orbit parameters could be determined by application of the procedure that was described in a paper given by Ninkovic in 2011. This was actually a basis of where I started with my research. So this is all presented, and there is a lot of formulas for this, so I didn't want to go into details about that part. So this procedure is based on simplifying on two simplifying assumptions. One is that the quasi-integral of motion for specific energy and the power law concerning the circular speed. So when we use these simplifying assumptions, this gets us in the way that we can calculate much faster the parameters for many stars, but of course we need to be able to check somehow if this is good enough, because it is some kind of approximation. So reliability of obtained results strongly depends on the quality of these assumptions. And for this reason, the motion of selected stars should be examined in this numerical integration that I have already done, and everything is presented in the paper in 2015. I have chosen to create a three-dimensional galactocentric orbits calculating basic Lagrange equations of motion for each sample star, and using the Runge-Kutta 4 method for these numerical integrations. In this way, I can see the orbit of each star separately. This was in the first step done on one smaller catalog. It's called SPOCS. It's spectroscopic properties of cool stars. This catalog consists of 1,040 nearby stars, but they are observed through big telescopes, and they have very good and very reliable data. These stars were actually observed through a exoplanet search program. So for 1,040, in total of 1,026 stars, there are all data that were needed for this analysis. In particular, position, proper motion, radial velocity, and distance. At that time, we used the distance from Hipparcos catalog, but today we plan to continue this work on the data from Gaia catalog. This is just to show a few examples of orbits of disk stars. So this is obviously a classical boxy orbit that is defined well defined in literature. You can see that this star is not going too much from the plane. Actually, it's just a few parsecs. This is another star. It's a little bit wider, but still this is a very well-defined disk star. Just for a comparison, I will show you one typical halo star that you can see can span from 4 to 18 kiloparsecs in the orbit. So what were the advantages and disadvantages of this approach? On one side, we have a method that can very fast and what we proved very reliable estimation of RM and E and max. And on the other side, we used this numerical integrator to calculate very well defined RP and RA, which is, for example, visible here. You can see these lines are very well defined. The orbits of stars are here when you look at the orbits. But on the other side, you are using a lot of computing time, and it is possible to do on smaller catalogs. But if you try to do this procedure with calculating orbits on a much bigger catalogs, like for example Gaia currently has data for 7.2 million stars with the radial velocity and everything that is necessary, but in future they say that final release will have 150 million of stars. So in the case you want to calculate orbits for 150 million of stars, you would need a very powerful computer. This was, let's say, a motivation to do this kind of research, where we can calculate much faster orbital parameters for disk stars. And here it's presented. I'm sorry, this is in Serbian. These graphics are taken from my PhD. This is the KS test showing that the distributions of eccentricity are well. In the comparison, they show good agreement. So the next step was to choose a few more values that needs to be tested and calculated. This is planar and vertical epicycle frequencies and local angular velocity. They are all related to derivatives of the second order of the local potential, and can be used to test shape of the potential from stellar disk samples. And if we assume an axisymmetric potential, which was done, and we allow a mixture of independent ellipsoidal velocity distributions, then we can get to these equations. Of course, we need to again use this approximation that for each star Rm is, let's say, similar to our sun. And if we are investigating the stars in the solar neighborhood, and we separate only the disk stars from that sample, then we can use this, and we can get these equations for Orth constant and planar and vertical epicycle frequencies. In order to do the first step was to describe how the local constants and potential is related. And first approach for disk stars involves use of this epicycle approximation in order to model the distribution of star eccentricities. The second step consists in studying how velocity distribution and eccentricities are related. And we analyze how these relationships constrain the ratios of semi-axis of the velocity ellipsoids. And it is necessary to adopt a more general approach than the classical epicycle model, because if we want to consider the asymmetric drift in our stellar samples, this was necessary. So that's what we have done also. So here are also some equations. The alpha here that you can see is the same alpha as before, as it represents the relation between Earth constants A and B. In order to do this, we needed a bigger sample of stars, of course, the realistic sample. We chose Geneva-Copenhagen survey, which was presented by Nordstrom in 2009. This catalog consists of 16,682 stars. It is one of also very complete catalogs like Spock's, but for the small volume, for the small limited volume of the stars in a solar neighborhood. We made two samples. One that was selected in both ways. We wanted to just select disk stars, and these are parameters that we use to limit these samples. Sorry. After we made these samples, the third step was to obtain the local galactic constants from nested subsamples. We needed to do these stellar subsamples in order to get planar and vertical electricities. So we chose two families of nested subsamples, were selected which were selected for decreasing planar and vertical eccentricity, and we used them for relation between mean square planar and vertical electricity and velocity dispersion. All these results are presented in the paper done with my mentor and a colleague from Spain who worked with us on this. This is just to show you how some of these parameters, how it looks. So you can see all the nested subsamples for eccentricity. We start with the total number of 12,000, and then you can see how it changes and what we get for the values of U, V, and W. And here are the second order diagonal moments of for the velocities. This is for Z max. It's very similar. And what we did next was to in this final step was to deduce from these nested stellar samples planar eccentricity and other things that were possible to calculate. And in total, we found that this is the best value for planar eccentricity, which is 41.1 kilometer per second per kiloparsec, and for vertical frequency, vertical epicycle frequency, we have this value. We also could calculate the rotational component of the solar motion, which is very well in agreement with data you can find in literature. I mentioned asymmetric drift, and our model was also possible correct for asymmetric drift. And if you do that, then it's possible then to calculate these more a few more parameters that were necessary. And for example, rotation speed at the place of the sun, we got 148.2, which is maybe a little bit bigger value than what you can find, but in literature you can find everything between 210 and 270 or something like that. So alpha at the end was calculated by these models, and in the final value we decided to choose that 1.02 is let's say the the one that best describes the model that we chose. Thank you Thank you for your attention. If there are any questions, I will try to answer.
Thank you, Milan. Um, to all participants, please raise your hands or ask your questions in the chat. I don't see any questions for now, but I am a layman in your field, so I would like to ask a very, very basic question, and this is, what data do we need for example, for a single star in order to be able to calculate its orbit?
So that's a very good question, because if you don't have actually this data that we need is what makes so much problem in calculating these parameters, and the values that we got are completely independent of the research that is already known. So in that way, I guess that with new available data from the space telescope Gaia and some others, we will get even better estimates of this. So the necessary value, the necessary data you need is position, of course. You need a proper motion in right extension and in declination, and radial velocity, which is the hardest one to calculate. But as I said, Gaia at the DR2 calculated for 7.2 million of stars.
Mm-hmm. Thank you. Thank you. We have another question.
Mm-hmm.
It was from Tomislav Jurkic in chat.
Mm-hmm.
He asks, did you determine the uncertainties of the derived quantities?
Yes, we did that, and it's shown in the paper from 2017. I didn't show it here, but we did that also.
Thank you, Milan.
Thank you.
If there are no more questions, we will move on to the last lecture of this morning. It will be given by Dr. Slađana Knežević, also from Astronomical Observatory of Belgrade, and she will tell us about the diagnostics of cosmic rays in a supernova remnant. Slađana, please go on.
Good morning. Do you hear me?
Yes, we do.
Okay. So I will present our work on supernova remnant 0509 in the LMC. This work was done in collaboration with Giovanni Molino, Rino Bandiera, Steve Schultz, Glenn Van de Ven, and John Raymond. On the right side, you can actually see the remnant, the AGST image of the remnant in Balmer emission. This is pure Balmer emission shown here. So I'm working on Balmer-dominated shocks. These shocks are non-radiative and collisionless, propagate through partially neutral medium, and have very strong spectral signature, which is a double component H-alpha line. So we have a narrow component with a width of around 10 kilometers per second that is produced when cold neutrals, once overrun by the shock, are excited by hot protons from the post-shock, and broad component with a width of order of 1,000 kilometers per second produced when these cold neutrals go into charge exchange process with post-shock protons. Each line we basically represent with a Gaussian, and the line widths, shapes, and intensities give us information about the pre- and post-shock region, namely the temperature. Then we can determine shock velocity. Once we have proper motion measurements, we can get the distance to the object, which is not very well known for the remnants, for supernova remnants. Then these lines actually also give information about a level of equilibration between electron and protons. And also, if you have shocks that efficiently accelerate particles, this can change the observables, like the line widths and also the line shape. For example, if you measure that the narrow line component is broader than 21, the thermal width of 21 kilometers per second, which is defined by the ambient temperature of 10 to 4 Kelvin. That means that something non-thermal is happening that can broaden the line. Otherwise, temperature larger than that would leave the medium ionized, and we wouldn't see Balmer emission. Since the energy from the post-shock is channeled into cosmic rays, then you expect that the broad line width decreases. So our goal is actually to do geometrical and physical interpretation of measured quantities such as surface brightness, broad line widths, and the offset between the centroids of the two components. So we decided to observe the remnant in the LMC 0509. One of the reasons is that the narrow line width has already some indications of cosmic ray presence because it's measured to be between 25 and 31 kilometers per second. Then this remnant is very good. Well, one of the best candidates, since we know the distance to the LMC, and we have measured proper motion, so we can get independent estimate of the shock speed. Some information about the remnant. So the remnant is old, around 400 years, and the size is around 3.6 parsecs. It was observed before, so the broad component was extracted from this long slit, and only for the two smaller regions, the northeastern part here and southwest region here. And you can already see that the southwest part is very complex in terms of geometry, because you see projected shocks here. So the results Helder et al. Had 10 years ago is shown here on the left side. And you can see that the broad line is poorly constrained. Actually, there is a very low signal to noise. And this is not, it's not surprising, since the intensity of the broad line in this region is actually less than 10% of the narrow component. On the bottom right side, you can see how the broad line width depends on the shock velocity for different equilibration levels. So basically, everything below this red line, which is a full equilibration, would need some cosmic ray to be explained. And you can see the measurements from these two regions here. We put it on the plot, and so we, with the MUSE instrument on the VLT, will try not only to get better constraints on the line widths, but also we can actually cover the entire remnant. So MUSE has a special sampling of 2-point arc, 0.2 arc second, spectral resolution of around 100 kilometers per second. So meaning that we cannot resolve the narrow line, and a large field of view of 1 by 1 arc minute. And you can see our results on the left side. We show a narrow line map, and the middle panel we show broad line map, and on the very right we show broad line map before stellar subtraction. So the field is crowded with stars, and as you can see here on the right side, and we have to do stellar subtraction in order to get as much as information as we can from these observations, so basically to go as deep as we can. The other thing that we have to take into account is that we see that LMC emission varies across the field, and you can see how it looks in different channels, like in H alpha, nitrogen 2, and S2 channels. So I will first present some results that we have from this northeastern part that looks like perfectly spherical. So we took spectra going from upstream towards downstream along circular axis, and we extracted profiles these arcs that are a width of 0.2 arc second. And you can see the results that we get. So this is the result of how the brightness of the broad component changes, then the measured width of the broad component, and the centered offsets. So if we apply a spherical thin layer model so we get that the best fit parameters are actually shown here, and the model requires actually that we have some density gradient along the line of sight, but also in the sky plane. So this actually Reno tried to explain only using geometry. So if this a change in the centered offset and width in the broad component can be explained only due to geometry. And we get that the shock speed is much lower than what's inferred from the proper motion, meaning we get the shock speed around 4,000 kilometers per second, while when we do proper motion measurements and the distance, we get around, well, more than 6,000 kilometers per second. So we'll see if that can be explained as a consequence of the velocity dependence of the cross sections, meaning that the observable mean velocity of the hot neutral may be significantly different from that of the ions. Or we might actually need some physics involved here to explain the results. So Hovey et al. Measured proper motion around the entire remnant. And you can see their results, so like how the shock speed changes with position angle here on the right side. We try to cover these same regions here and extract the profiles and get the line with centered offsets and the density ratio of the lines. So you can see one of our spectra, which is actually from the region, which is the same as Helder et al. That I showed in the beginning of this, from the long slit of this northeastern part region here. So where they couldn't actually constrain, where they actually had very poor signal to noise in the broad line. So we managed to get results for 38 segments out of 44. And out of these 38, 5 have low signal to noise in broad line, and they are shown in this plot here as green points. So here I show the measured broad line with the position angle. So if we want to give some physical interpretation of the results, of course, as I said, we will first try to work on the geometry and then put some physics in. So on this plot that shows how the broad line width changes with shock speed. So I put our measurements here. The solid line is where we have poor equilibration between electron and protons. And the dashed line is with full equilibration. This is from Molino et al. Shock model. This is also, these lines are also without cosmic rays included. So basically everything below this dashed line would need some cosmic rays to be explained. But as I said, like first geometry, then physics. So this work is still in progress. So I mentioned that so we have, well, for us, that's large field of view, but, I mentioned that it's crowded with stars. And apart from that, I mean, I think we might have detected a new source. So I show here a different, well, 12 different consecutive wavelength slices of the data cube. So below this red arrow, if you follow it through the images, you will see in the beginning there is nothing. that you can see in the image, then you start seeing some point, and then it disappears again. So when I took the spectrum of it, and which is shown here in this green line, and I put it in the MART software, which is the software that compares your source spectrum with several templates. Templates are there are 5 templates for the star, 6 for galaxies, and 1 for AGN. So this is a very useful tool to as a first guess to identify the nature of the source and to get the redshift. I get the best match for this spectra is that it might be high redshifted star forming galaxy at the redshift of around 0.7. And basically that's all I wanted to tell you about. So thank you for your attention.
Thank you, Slađana. Please ask any questions in the chat or, oh, I see a raised hand. Jelena Kovačević wants to ask a question. Also, Sohan Jita, I apologize if I mispronounced that. Can the moderators please give the word to Jelena?
Vladimire and Stanislav, can you give the word to Jelena Kovačević and then to Professor Zohan Jita, please? Jelena, you can now unmute yourself. Thank you.
Okay, can you hear me?
Yes.
Yes.
Great. Okay, I have one question for Slađana.
Yes.
So this is very interesting for me because I'm doing AGN spectra. And I want to know, can you see in supernova Raman spectra also broad age beta, not only broad age alpha, or it is too low to be seen?
Well, it's fainter than age alpha, and actually in this data we do see.
So you cannot see in this data, right?
Yeah, we see it in this data, yes.
You see it.
Yeah. It's, we will need to combine more spexels to get better signal to noise, so it won't be with the same spatial resolution, but it's we see it.
Okay, so pity that you don't have some picture where we can see both broad age alpha and broad age beta.
Yeah, well, yes.
Okay, nothing. Thank you very much.
Welcome.
Bye.
Professor Zohan Jita, you are permitted to talk. Please unmute yourself. Hello?
Hi.
Hello, welcome.
Hello.
Oh, thank you. Thank you. Oh, okay. I'm not an astronomer, but I'm curious. How do you find a star, particular star, the one that you showed in the very last slide? I mean, do you have a computer program looking out for these rising stars, so to speak?
Okay, so no, I mean, I wasn't looking around the field at all, but it pops out when I did stellar subtraction. And when I looked into the data cube, then I saw it. I mean, these images that I showed are like, this is without stellar subtraction. So actually it's by accident. I mean, I wasn't looking for any other source. I was just looking in the supernova remnant, and then since I did stellar subtraction and just looked in the cube, I mean, just sliced over all channels, I noticed something.
Oh, great, thanks.
Welcome.
Well, thank you again, Slađana, and thanks again to all the speakers of this morning and to all the participants for the discussions. This is the end of this session, and we should reconvene in 25 minutes at 11:15 for
Yes.
the